The first paper is on flutter echo modeling. Flutter echoes are considered as a bug in the design of auditory spaces, but the authors of this paper, they consider it as a feature rather than a bug. And the paper on flutter echo modeling is authored by Gloria del Santo, who will present, by Karolina Prawda, and by Vesa Välimäki. Please go ahead.
Thank you so much. Okay, then let's begin. So first of all, flutter echo. He already mentioned something, but let me describe it a little bit more. It's a phenomenon that occurs when sound waves bounce between two parallel reflective surfaces, creating a repetitive sound. And to give you an example of flutter echo, I'm going to first play a dry drum loop, or an echoic drum loop, and then the same drum loop convolved with an impulse response that has flutter echo in it. Cool. Okay, you can hear it particularly when the drum loop stops and we can hear better the tail of the impulse response. So the objective of this work was that of recreating flutter echo as an audio effect, starting from known room geometry and from measured room impulse responses, and we wanted to limit ourselves using only simple DSP blocks. This is actually can be seen as an extension of the work done by Tor Almröst at the DAFx 2015, and where he presented a two-panel setup in an echoic chamber, and so flutter echo in this particular case of two panels parallel to each other. While we are going to study flutter echo in rooms. So throughout the presentation, I will always mention this impulse response that was measured at the Variable Acoustics Laboratory, ARNI, at the Alto Acoustics Lab. The peculiarity of this laboratory is that the walls and the ceiling are covered by variable acoustics panels that have slots that can be opened and closed to let the sound get in or reflected. And inside these panels, there is absorptive material. So essentially, what we can do in this laboratory is to get a repetitive, and a reflective or absorptive property that we want. So in this case, to measure this room impulse response, the panels in these two walls were closed, while the other ones were open. So let's listen to the impulse response. I'm going to play it again because flutter echo here is quite subtle, and it's high in pitch. So what we want to do is to synthesize this. So our algorithm needs some input parameters, and the first one is repetition time, which is the time that passes between occurrences of flutter, and essentially is related to the distance L between two walls. And to kind of picture it, let's imagine a sound source between the two walls that generates two pulses, one towards the leftmost wall and the other one towards the rightmost wall. And repetition time is the time that it takes, the time that it takes for these two pulses to bounce on both walls and come back for the second time at the source position. So whatever the receiver is, it will hear a sequence of 4 pulses within TR seconds that we can also see here. Cool. Let's go and take a look at the energy decay curve. So what we noticed is that in the frequency where flutter is, we can observe a dual slope energy decay that can be we can find the two components using Bayesian decay analysis in this case. And the first component can be associated to the early reflections and diffusive reverberation. And the second one is associated to the reflections of the echoes, let's say, or the reflections associated with flutter. So if we zoom in the region where the second component governs the energy decay curve, we see this sort of decay. It's a step decay with the step length related to of about TR seconds. And finally, the reverberation time dependencies over frequency. Here I'm going to mention once again Tor Almrost. In his case, in his paper, he used the Coul's equation to describe the T60 curve. And what the Coul's equations say is that for the case of a parallel finite surfaces with free edges, the T60 curve can be decomposed into these three components. The first one accountable for the diffractions at the edges, and it affects mainly the low frequencies. Then we have a second component for the absorption at the surfaces, and then a third component for the air absorption. And essentially, the T60 curve will look something like a bandpass filter. And Tor Almrost also introduced the concept of FLUTTER tonality, which is the result of a gradual bandpass filter effect of the partials of F0, F0 being the reciprocal of the repetition time, the first parameter that we saw. And essentially is the frequency at which we have maximum T60. Since now we are talking about room impulse responses, we have also to take into account room modes and diffraction patterns. So what we want also to capture from the reference room impulse response is these dips in the curve that are around long ringing modes. So how do we estimate these parameters? For the first parameter, the repetition time, or TR, we can use the energy decay curve. So what we are going to do is to average the time that passes between points of steepest decay. And we can to find these points, we can use the estimated derivative. While since the T60 curve resembles a bandpass filter, what we need is just the bandpass gain and the frequencies of -3 dB. And for the ringing modes, we can what we did is to put ourselves at a point in the later reverberation and take points of maximum in the magnitude response. Of course, we cannot take all the maximum, so here we applied a window, a sliding window. The details of which are, like for example, the length are in the paper. And finally, since we want to model a specific source and receiver position, what we did is to take a snapshot of TR seconds. So here you can see the waveform. And to get at the noise version of it, we project it onto the wavelet subspace. Because you will see afterwards, we are going to use just the envelope of it. OK, so this is our algorithm. Let's forget about the decimator and the interpolator for the moment, and let's focus on this part here. This structure resembles the structure of general pseudo-random reverberators. And we have a delay line in the, so in the feed-forward path, we have a delay line for the modeling of the repetition time. Then we have an attenuation filter divided into two components that we're going to see in detail later. And then we have a velvet noise sequence that shapes as sparse FIR filter, sorry. Why do we, so we use this structure because when it was used in the modeling of late reverberations, this was known to cause some repetition in the output. And for diffuse late reverberation, this is something that is unwanted. It's diffuse, so why would you hear a repetitive sound in it? And this was caused mainly by this filter because it didn't change the sequences, it didn't change its coefficients, so they were like kind of reused. And instead of trying to solve this problem, we want to exploit this problem, because what we want to do is to synthesize something that is really repetitive. So that's why we use this structure. And then for the modeling of the early reflections and diffuse reverberation, which then complete the room impulse response, we use an FIR filter. So this is actually like a suggestion from a reviewer. So, so thank you if the reviewer is present here. FLUTTER Echo covers mainly frequencies below the 3 kilohertz or 4 kilohertz. So we don't need to synthesize them. So we can, in our case, we can work at lower sampling rate. And so in this case, we move from 44.1 to 8.82 kilohertz. Then the bandpass filter is designed as a combination of a low pass and a high pass Butterworth filter. And then to model the ringing modes, we use a ripple filter that introduces to the magnitude response of the bandpass filter a sinusoidal variation with maximum at these lowest decaying modes. And finally, the sparse FIR filter has coefficients that are taken from a velvet noise sequence and that are shaped by, from the envelope function. So we apply an envelope functions on the VNS, and this envelope is the envelope of the projection of the waveform that we saw earlier. So let's hear some results. I'm gonna play only the drum loop because I don't know if I have enough time to play everything. So the first one will be the drum loop convolved with the measured room impulse response. Okay. Okay, the pitch is not exactly similar, or they're not the same. And this is probably because of this dips in energy, because we didn't, we think that those are not from the FLUTTER Echo, but are rather from some objects in the room, and we didn't model it. Our algorithm wasn't designed to model these dips in energy. So that's why we measured another room impulse response. And this one is from a bigger room, has a longer FLUTTER Echo with larger, bigger repetition time. This is the same as the one that you heard at the beginning. So we are much happier with this result compared to the first one. Let's take a look at the repetition time. So for frequency, for almost all the octave bands, the difference between the reference reverberation time and the synthesized one were always below the just noticeable difference of 5%. Apart from the 125 octave band and 250 octave band for the case of the high voltage room. But we are not too worried about this result because in these frequency ranges, we don't have FLUTTER Echo, and this error is due to the FIR filter that models the early reflections and the diffuse reverberation. While for what concerns the repetition time, it was modeled with an accuracy of an error, sorry, with an error of less than 1%. So in conclusion, we presented a new method to synthesize FLUTTER Echo from known room impulse responses. We have an accurate control over T60 or reverberation time and the repetition time. The modeling of the pulses has been done using shaped VNS or velvet noise sequences. And one of the downsides of this approach is that to get complete room impulse response synthesis, we need this FIR filter. We need a way to assign the coefficients of this filter. And this was, in our case, created this discrepancy in the repetition time for some frequency bands. As future work, it would be interesting to go on with this research and to get a better understanding of the perception of flutter echo, to then be able to design a perceptually driven synthesis algorithm instead of an algorithm based only on T60 and repetition time and the pulse shape. So thank you so much for your attention, and I want to also thank the Alto Acoustics Lab and Gianpaolo to allow me financially to come here. So.
Thank you for the presentation. Do we have questions? I might start off with one thing. I wondered, you have the distance between the parallel walls as a design parameter.
Yeah.
And I wonder how the other distances of the room, how the room size enters the design, just via T60, or do you have other distinctions between small and large rooms?
We use the distance between the two parallel walls because that's what, because it's what we need to model the repetition time. That's what we need essentially, because what happens is that we have this bouncing between these two walls, so we assume that there's no bouncing of the sound waves in the other dimensions. And then, yes, to take into account the room geometry, we use the T60, but that it's for more the decay, the attenuation of the frequencies.
Okay, so you just get these two as design parameters?
Yeah.
Okay, thank you. Do we have more questions? Here.
Could you go to the block diagram, please?
Sorry?
Could you go to the block diagram? I was wondering about the parameter lowercase r. Oh, no, like the diagram of the whole signal flow.
The block diagram.
Oh, okay. Yeah, sorry. I heard like bar. There you go.
This one?
Yes, I was wondering about the lowercase r gain, what the like physical interpretation of that, because it kind of makes sense to me that you have these delays as you go around and around for the like circuit time for one packet of energy bouncing between the walls, but I wondered why there was the feed-through term of lowercase r.
Lowercase r in the ripple filter.
Yes.
Yeah. What it changes is the amplitude of this sinusoidal behavior, and the more of it. Okay, now I think I have to refer to the original paper for this model to give you exactly the meaning, but we can, using it, we can decide how deep we want to go, essentially. But this Reaper filter has been used in the, by Vesa Välimäki and the sound synthesis of the harpsichord. So if you want to have a better understanding of it, either we can talk later or there is this paper.
Okay, thank you.
Okay, one more quick question. No, then let's thank you again. Thanks for the